Ever since I read the HOMA paper, which attempts to replace the TCP with another protocol called HOMA in the data center, I've started noticing this term showing up everywhere I read. SmartNIC, or Smart Network Network Interface Controller. It's interesting because it drove me into a path where I things that I'm not comfortable with, things like the NIC, the Network Interface Controller. I don't know anything about what is going on in the circuitry of that thing. So spent few weeks researching these things, and when I did that, I noticed that while I know what a NIC does, the Network Interface Controller, basically the job is it does the networking, right? But to me and most of the audience of this channel, we're really interested in the truth behind everything. What is exactly what's happening, and that's basically what I want to explore in this episode of the Backend Engineering Show. If you love this stuff, consider subscribing. Enjoy the show. Check it out on Spotify, Apple Podcasts, all that stuff. And how about we jump into it? Welcome to the Backend Engineering Show with your host Hussein Nasser. And the network card, it's or the controller, it's the device that connects the machine to the network, right? And the first question is like, what does that mean, right? You see, a network could be run on different mediums, right? Ethernet is the common one. I suppose you can argue that Wi-Fi is the more common than Ethernet, but regardless, right? So we have many mediums. We have many physical mediums. That's fiber through light. We have Ethernet through electricity, and we have Wi-Fi through radio, right? Regardless, what's the physical medium, OSI layer 1, we don't really care in the application and the computing, When we look at things from the data link layer, everything becomes digital. And once it becomes digital, I don't care where you ship this frame or data to, right? Whether you ship it through fiber or radio or electricity, it doesn't matter. You're gonna reach the inside. And I think that's the smartest decision we made by creating that layer, okay? This abstraction, then we code on this abstraction, and we don't really care what is underneath us. Because imagine if we didn't have that, then we're gonna have a specific application for fiber and another specific application for radio wave, which is Wi-Fi, another app for Ethernet. That will be a disaster. I know that nobody can ever imagine this because, of course, I don't have to really care. But people, when they designed this, they actually actively thought about this. So we, as engineers, never have to worry about it. So I wanted to give some credit to the people who designed the concept of the OSI model, the concept of this layering, right? So that being said, the network card takes care of the physical layer. It transmits whatever we have in terms of bits to be specific, into the medium, right? But then the question becomes, what else the network interface controller does? And that's the question I try to answer, exactly what it does. Because you see, once you understand what the network interface controller does, then you start saying, oh my God, why is it doing that? You start asking these questions like, why is it doing this, and why we are not doing it this way, And then this question of why will be answered with obviously tons of papers and research, because people have been diving into this thing. So what happens? What is the network interface controller does? It takes care of the modulation that we talked about, the conversion, right? From the bytes, from the bits to the physical medium, and vice versa, for the physical medium down to these bits. But still, that's not enough. There is another layer on top of that, which is called the data link layer. The data link layer converts whatever the application sent it, and we're going to talk about what the meaning of application here, down to this data link. And think of data link layers has some of its own headers, So frames, so MAC addresses, right? So each network controller has a physical unique address associated with it. Okay? And when we send a frame, you specify where this frame is going to, the physical destination MAC address, because network cards usually just talk to another network card at that layer. They don't talk to the internet directly, right? It's designed specifically to hop by hop communication. Okay? So if I want to send a frame, you have to specify where this frame is going to. That's it. At that data link layer, we don't know anything else. There's no concept of IP addresses. There is nothing. There is no HTTP. There is nothing. No, everything was encapsulated into a frame. And then the destination MAC becomes that, and the source MAC becomes the address of that frame, right? Where this machine, where this physical network address card actually exists. And when we think about it this way, then interesting things happen, right? We're going to take that MAC address, the destination, and the source, and then put whatever the application sends us into that frame, and the whole thing becomes a bunch of bits, and the bits will be transferred into the network card, and the network card will convert into either electricity, Ethernet, radio wave, Wi-Fi, or fiber optics. If it's you're connected to have fiber optics, right? Light, effectively. And so it does two jobs by default, the traditional NICs. If I receive a bunch of light signals or a bunch of electric signals through the Ethernet, or a bunch of radio waves through Wi-Fi, then the job of the network card is to convert this bunch of noise into something meaningful at the data link, right? Which is the frames we talked about. So once it does that, it will detect a frame. It will say, okay, this is where the frame starts, and this is where the frame ends up. It knows where the frame ends and the starts, because it will continuously look for this stuff. And guess what? It's going to arrive. These frames will be arriving all the time. Some of these frames will be destined for this machine, for this network card. Some of them will not. Example is the Wi-Fi. As I'm speaking right now, there is a bunch of radio waves around me, and my Mac in this particular case, or my phone, is constantly getting these radio signals and converting them to frames, only to find out some of them might be addressed to me, some of them might be addressed to my routers over there, right? There is no path when it comes to radio waves. Like, oh, I'm shooting directly at you. No, it's everywhere, right? So my phone literally picks up everything. Yeah? But my network card that is baked into my Mac and the phone or all this stuff, it has a filter at the data link layer. It says, okay, is this frame, the destination MAC for this frame, is it for me? If it's yes, then it will pick that frame, remove that MAC address, destination MAC, right? And then whatever the content of that frame, ships it to the operating system, right? What does that mean? It means that the network card has that now. And what does it mean even to have that? Is there a specific memory location? Is there a buffer where the network card stores these frames? It has to. It can't be in the air, right? You might say, why don't we use the host memory, right? Which is the computer. We can use the host memory. We can do that too, right? Regardless where we store this temporary frame that we're about to ship to the operating system, the CPU needs to move that to the main memory in order to process it, right? Otherwise, it doesn't exist. And just by looking at what does that mean, there are many ways to do it here. You can do something called the interrupt, where the network card will have the concept of an interrupt handler, which says, hey, CPU, it will talk to the CPU of the machine. So the CPU that I have on my server is being bothered by network activity. Something I never thought about before. Never. Right? Network engineers might yell at me and they say, hey, of course. How else do you think is happening? But no, actually putting it in words and listening to the words and listening that actually the CPU is doing work for this thing, that means part of the CPU is being used for this activity. All right, regardless. So let's do the interrupt handling. Talk to the CPU. Hey, CPU, I have a frame for you. Pick it up. So the CPU, based on this priority, will stop whatever it's doing, right? And you might have 8 cores in your CPU, and then the network card will pick whatever it was assigned to and will say, hey, pick this frame. And the frame will be picked and the data will be delivered to the OS. The OS now knows that it's a frame, so now it up to layer 3, which is what? The IP layer, or the Internet Protocol. Okay, what is this? It has to be an IP. Right? There is nothing in the internet other than IP, okay? At layer 3, as far as I know. Okay? So IP, well, how does the IP look like? Oh, there's the header. It's 20 bytes. Let's slice and dice it. Oh, this is the source IP address, destination IP address. Start knowing all this stuff. And then if it's a TCP protocol, we'll look at the protocol bit in the IP header and says, oh, this is TCP, oh, this is UDP, or this is SCTP, whatever the protocol is. All right, let me just crack it up a little bit and then look at the content and then deliver the content to the higher layer, which is your application. So which port this is destined to, port 80, port 443, and we'll do all this stuff. So there is a lot of processing doing. Yeah, if you have receiving a bunch of couple of frames, sure. But imagine a data center where there's tons of billions, literally, of packets being processed maybe every minute, right? Maybe I'm a little bit exaggerating, but you get my point. Then imagine the amount of processing that the CPU is actually doing here. It's quite non-trivial, right? So what do we do here? Okay? So we talked about the network card does 2 jobs here. The transformation and the filtering for the MAC address. That's the only 2 things it does today, right? There is a mode, by the way, you can put the network card on, where we talked about, like, if you received a bunch of frames, if those frames are not destined to you, right, which you're going to receive from other stuff, right, those frames will be dropped right there and then. The OS will never know about them, right? An example is like my Mac is dropping frames all the time because there are frames being sent to other machines through my Wi-Fi network, right? But my Mac is dropping them because the destination Mac is not destined for that machine. So the network card actually at that layer is dropping it right there. So the OS will never know of them. There is a mode you can put the network card on called the Promiscuous mode, which means it doesn't discriminate against frames. Any frame, take that frame, just ship it to the OS. I'm not gonna even look at it. So slightly faster at the network card because, hey, I'm not doing any processing to look up these frames. I'm just delivering everything to the OS. So obviously slightly no processing at the neck, but all the processing now becomes in the OS, right? Which adds overhead to the OS, and overall is all overhead regardless, right? So what we want to talk about is the smart concept of NIC. The SmartNIC becomes then a way to push the logic that we're doing in the OS even more down to the network card, so that we do not bother the network card. We don't not bother the host CPU with network interrupts, with network processing that are non-trivial, right? Can this be done in the CPU? Can I shift the entire TCP IP stack down to the NIC? And this is something I've been done for a long time. There are obviously advantages, there are disadvantages for it, right? And that's what we're talking about, the SmartNIC concept here. And that's what the HOMA paper tries to solve as well. Because if I can do this parsing logic, right, and give the application exactly what it needs without any additional processing, because today you have to do a lot of processing. The OS has to filter the port. The OS has to, do the checksums. I believe even the NIC has to do the checksums, right? The checksums for the frames, I don't believe it's done in the NIC. I don't think the NIC is capable by default doing these checksums, because that's an additional processing. The CPU is being hired to do these jobs, the checking the length, checking invalid headers, and all this stuff is being done by the OS. Check the destination port, check the source port, filter anything, do the calculation, maybe merge different segments together when it comes to CCP. With the networking cards now, and this is what is being happening right now, the smart NIC industry is being exploded. They predict 40%, around 40%, market share when it comes to by 2026, according to an article I read. I'm going to reference it below. So pushing things down to the network card to do not only just the parsing, even do the handshake for the TCP, do any processing for the UDP side, and advanced protocol as well, right? If you can do that, all that stuff, even maybe TLS in the future, then the OS will receive a clean data that the application immediately just takes and process. The CPU, cost, all the CPUs that you have, if you have 10 cores, all the 10 cores will be just used for the tenants that live in this machine. This matters if you have like a virtualized environment, of course, right? It matters really big, right? But otherwise, you have to reserve 3-4 cores just for the network processing, just for this task, right? And there's a formula. I think 1 hertz of the CPU time is used by 1 bit, right? So if you do that formula, so that means if you have like if you have like a 1 gigabit Ethernet, right? Then you need 1 gigahertz CPU, right? So the dedicated 1 gigahertz for one, right? And if you have like 5 gigahertz Ethernet, then you need a 5 gigahertz CPU, which I don't think it exists. I never seen a 5 gigahertz. Maybe I'm wrong. So you need maybe two cores of 2.5 gigahertz each, right? And then it starts to add up. So now there is an overhead for processing networking, and people are trying to push this stuff to the SmartNIC. So advantages, obviously performance, and now all the CPU, a beautiful CPU, is available for MOA and MOA only. But here's where the problem lies. I'm not sure about future upgrading and maintenance, because now you're making the network card do more work. So you need a CPU. So obviously the price will hike up, right? The network cards obviously is going to go skyrocket because it's very expensive to put CPUs and memory. You need its own memory, unless you can do a direct memory access probably to the host. But you need its own processing. And when you do that, then it requires more money, more problem. And when you do that, you put firmware in the network card, right? And firmwares are really hard to patch. So if you find a bug in TCP or anything related to the implementation of TCP IP stack, you have to patch, not the operating system, which is kind of trivial. We know how to do it, right? To patch OS, like there's a new version of OS. But it's a hardware thing now. How do you patch the hardware? It becomes really interesting. I believe there's this programmable chips that you can easily program. But this is a completely new thing. So whoever designed this thing, probably they have plans to have a completely different patching framework. And there is the vendors now. The vendor for this particular network card is different than the vendor, so they have different software. Will there be a standardization like we do with the operating system, which we standardize pretty much on Linux right now, right? So it becomes very interesting. I think it's a very interesting field, but it won't be without its own problems, right? I'm just interested to hear your thought. What do you guys think about the concept of SmartNICs? Let me know in the comment section below. For those who are watching on the podcast, thank you so much for your support. Appreciate you. Give this video a like. Give this podcast a rating if you like it. And I'm going to see you on the next one. You guys stay awesome. Goodbye.